to get for the angular velocity before and the angular velocity afterwards to see if we can work out what happens to the angular kinetic energy before and afterwards, and see if we can account for the difference between the angular kinetic energy before and afterwards. So the measurements that you'll have to take is you're going to have the roundabout, and you're going to have 3 or 4 people on the roundabout, and they're going to be trying to hang out as much as they can from the roundabout just to start the thing going slowly. Whoops, headless roundabout people there. So the things that we'll need is the mass of everybody that's going to be taking part on the roundabout. We'll need to know the radius beforehand on the roundabout, and we'll need to know omega when they're spinning around first. Because the roundabout isn't frictionless, and therefore there's an external torque applied to it, we're just going to try and time 2 rotations. So it's going to be 4 pi is the total divided by the time, 2 times the time that you measure. So we're really timing 2 rotations and dividing by the time for 2 rotations, and that should give us omega. Okay, so 4 pi is the total angle that you go around, and the time we're going to divide by 2 to give us the time for 1 revolution per second. Okay. The people on the roundabout are then going to be asked to get close, I mean like real close, by pulling themselves into the roundabout and trying to concentrate their mass as much as possible. So you'll have these lucky people getting really close here in the middle of the roundabout. To concentrate the mass much smaller, we're going to have to measure the new radius there, R2, and the mass will hopefully stay the same. But that's going to change the total moment of inertia. What you're going to have is that the total moment of inertia here times the angular velocity, so I1 times omega 1, should be equal to the new moment of inertia that you've calculated here, I2 times the new omega 2 here, because you'll need to, again, work out the time for 2 rotations, or maybe even 3, depending, because they should be going faster at this point. So we'll say 2 rotations divided by the time there, and put that into that equation there. In this equation, for instance, the total moment of inertia to start off with, so I1 is going to be the mass of person 1 times their radius squared, plus the mass of person 2 times their radius, plus the mass of person 3 times their radius squared. There's also going to be the moment of inertia of the roundabout. That's going to appear on both sides of the equation, and then we'll be able to work that out as an unknown in the equation to work out what the moment of inertia is of the roundabout itself. Because we don't know the mass of the roundabout, I don't think the council would be happy with us unbolting it, taking it away to weigh it, and taking off the handles and things to weigh those and get the mass of the roundabout itself. So that should give us the moment of inertia of the roundabout by that sort of process. We're assuming that the total momentum before equals the total momentum afterwards. What's going to be the errors in this procedure? Why is it not actually done? Yeah, because the external torque provided by the friction in the bearings is going to slow it down considerably, even though we're trying to make it speed up by decreasing the moment of inertia. The second thing is that we're then going to try and work out the kinetic energy before, so the half I omega squared from the moment of inertia there, half I omega squared before for the kinetic energy, and then the kinetic energy afterwards, half I omega squared 2. And we should find that that is bigger than that, which is quite different to anything you had in collisions with linear air tracks and things like that. And we need to try and explain why there's this increase in rotational kinetic energy. And hopefully the people on the roundabout will be able to give us an idea of why there's that increase in kinetic energy. But that's why we're going down. That kind of speed, so if you hang yourselves right out if you can. So if you start hanging that out. You just do 1 revolution. So you're going to move in after 3. 1, 2, 3. 67. 76. Okay. So you'll add those up and we'll get a total mass. If we say that the radius beforehand, R1, was 1.3 meters, radius at the end, we didn't actually measure, but I think you'd be looking at about 0.4 meters for when you were as close in as you could. Uncertainties obviously here at 20% because we're plus or minus 0.1 meters in 0.4. We're dealing with quite large uncertainties, so it's really orders of magnitude. Now for omega 1, time for one revolution for when they're strung out? 11.3 radians per second, is it?
No, it took 11 seconds.
11 seconds for one. So 11 seconds for one revolution. So you can work out the time for one revolution, for 1 radian per second from that. And after they'd speeded up? 4.6 seconds for one revolution. Is that for one revolution? 4.6 for one revolution? Okay, 4.6 for one revolution. So that's all the results that you need there to be able to work out the angular momentum before and the angular momentum after. What you're going to have to leave is the angular momentum, as the moment of inertia rather, of the roundabout as an unknown in your equation and solve for that on both sides. This is very similar to how the skater not only manages to increase her angular velocity, but also her rotational kinetic energy by doing work, by pulling in her arms and legs in the middle of the turn.